or mean point also will be varying. So if you look at, we have given this random variable follows this normal distribution with mean mu and variance sigma square. We need to give only these two numbers. Based on that, we can get the picture. And instead of dealing with infinite number of pictures, we would like to convert any given normal random variable to a new normal random variable with mean 0 and variance 1 square. For this, we have used this transformation encircled below with red color standardization process, standardizing any given normal random variable into a standard normal random variable. The advantage is that we can use the already calculated, the tabulated values. Look at the first note in the top line, the very first line. You ask me any probability in terms of the actual random variable, normal random variable, capital X. We can use the transformation and we can convert the problem into finding probability for a particular value of the standard normal random variable. We have given two examples in the right side. And also we have discussed one problem and then exponential distribution. You have any doubts so far? Anybody can tell me that. If you have any doubts, we shall discuss that. To summarize the first unit, maybe we can look at the syllabus also. We discussed probability, and I have given some 15, I think 15 problems regarding probability and random variables, I think. And then we have discussed mean, variance, median, mode, standard deviation, some useful numbers about additional information of probability distribution, how to find those numbers, quantifying the nature or behavior of probability distribution. And then we have seen some special distributions, binomial, exponential, normal. The first two for discrete random variable, the remaining three for continuous random variable. With that, we completed the unit 1. Now, we would like to study about unit 2, Chebyshev inequality, law of large numbers, central limit theorem. These formulate, are these two related to probability again, whereas this part is related to estimation, is related to statistics. Look at the course name, probability and statistics. So far we discuss only probability. Statistics will be discussed after 2-3 days, maybe from the next week, or if possible in the last class of this week. Till that we shall discuss probability. First we shall look at this central limit theorem. Then we shall discuss about Chebyshev inequality and the law of large number. Anybody heard about the central limit theorem? So from here we discuss about unit 2. Okay. First, let me talk about, actually the central limit theorem is closely related to this normal distribution. Central limit theorem and normal distributions are related. I'll tell you how. Before that, let us look at one example as usual. Always we motivate or we explain our strategy or the idea with the example so that we can internalize, we can realize that properly. Suppose if I have one random variable, Okay. And it is having a probability distribution. Suppose if you have another random variable, I say this is first random variable, this is second random variable. Now I say that both of them are having the same distribution. Another random variable. Many random variables I have. Can you give an example for this situation? Many random variables with same distribution. For example, many random variables with Bernoulli distribution. Let us consider that. Can somebody give one physical real life example for whatever I say? N random variables. Each random variable follows Bernoulli distribution. Can you tell me that? Some example just to try for that. So far we discussed already. Quick.
Toss a coin.
Toss a coin. How many times? N times you have to toss.
Yes, sir, 10 times.
N times. So then I understand that each toss is following a random variable that is a Bernoulli random variable, and this is Bernoulli distribution. All those things I can talk about. Suppose if I assign a number for head, I am giving a number. For tail, I am giving a number. Say for example, suppose if I say that whenever I get head, I am writing 5. Whenever I am getting tail, I am writing 7. Some numbers I am saying. The same thing I am following for all the n tosses. Okay. Now, meaning this capital X can take this capital X1, X2, X3, X4, Xm can take only two values, each of them, either 0 or 1. That's what we were discussing on those days. Now I said 5 or 7. Whatever number you are asking, that doesn't matter. Only two values it can take. Whenever we talk about random variable, we are assigning numbers to the random variable. That's by definition. Now I'll talk about what is capital X. Or instead of asking you, I am defining capital X is the average value of these values. Average of the summation. Because I know that each random variable can take either 0 or 1 in the earlier examples. Today I said 5 or 7. They can take only two values, okay, success or failure, head or tail. For that I'm going to assign a number. I'm considering the average. Okay. This capital X is my new random variable. The reason is that the value is depending on these random variables. I'm asking you what is the probability distribution of my new random variable. This is our today discussion. Let us look at an example for x1, x2, x3, xn. Okay. Then we shall try to draw the pictures. Then we shall try to conclude. Okay. First, let me take these x1, x2, x3, xn are appearing in exams. Success means passing the exam. I am giving grade 1 or 1 grade point I give you. Failure means getting failed in the examination. I give you 0 credit points, either 1 or 0. Or you just think of taking attendance in our class. If you are present, 1 point is given. If you are absent, 0 point is given. There is no in between values I give you. Okay. Now, how many examinations you appear? That you have to decide first. Or in other words, for how many students I talk about this attendance situation. Say, for example, let us fix one example instead of jumping examinations and attendance. Suppose if you, there is no difference in that. Okay. Suppose if I talk about mm, exams, let me consider mm, x1, x2, xn. One more thing also you will write. Either say I'm talking about n exams. Okay. We are talking about n exams, and each one is Bernoulli random variables, xi or Bernoulli random variables. I is actually from 1 to n. Okay. Xi can take values from 0, 1. Usually we write either 0 or 1. Anything is fine. These are the situation what we have. Xi can take values from 0, 1. 0 refers pass. 1, oh, sorry. Even if we write that also, that's fine. 0 refers fail, 1 refers pass. Fail or failure, pass or success. These are the things whatever we have discussed so far. Just I'm interested in the definition capital X equal to the same definition. Maybe we will write here also. Okay. Now, suppose if I appear in one examination, what is the probability distribution? Then I have to talk about probability also. Capital X can this capital this. Suppose if I appear in one examination, what will be the probability distribution of capital X? It is simply the Bernoulli distribution because only one examination appear. Suppose if I appear in two examinations, okay, this x1 and x2, and after that I can compute this average as I defined already. Okay, only two exams, both may be failed. One failed, one passed. Okay, one passed, one failed, or this, or both are passed. These are the possibilities. So if I consider the average, it is 0. For this, it is 1 by 2. For this, it is again 1 by 2. For this, it is 1. What do I have here? This are the possible values for this capital X. the possible values. Okay. Now we have to draw the probability distribution for these possible values. Maybe I'll observe possible values for capital X, or what are the possible values? 0, 1 by 2, 1 by 2, and 1. Only 3 values are possible. Suppose if I want to draw the picture, the probability distribution, okay, this is 0, this is half, this is 1. Okay, maybe we will use the same color. What is the probability for 0? That's my question. Out of the 4 possible values, 0 occurs only once. We observe that probability for x equal to 0 is 1 upon 4. Probability for x equal to half. Can somebody tell me what is the probability?
Half.
Very good. 2 upon 4. Half. What else is remaining? What is the probability for 1? Among the 4 possible cases, only once we are going to get this 1. Now I'm going to mark those things in this picture. 0 is 1 by 4. 1 also is 1 by 4. Half. For that, the probability is half. Here we are looking. Let us look at an example. Discrete case. We are not looking at continuous random variable. Involving discrete random variable. The same thing can be discussed in continuous random variable also. If I discuss that, the picture will not be like this dotted places. It will be a curve without a break, a continuous curve. This same idea I have to apply for 3 examinations. You see, I am not looking at probability for pass, probability for fail. I am looking at what is the probability for the new capital X I have defined. Let us follow the same. Let us follow the same idea. Okay. Now you can tell me. I hope you will try for that. For n equal to 3, then I have x1, x2, x3, 3 possible x1, x2, x3 I can have. Then I can talk about x also, which is the average of all these 3 values. How many possibilities are there? Can someone tell me?
8.
Each x1, x2, x3 are having 2 possibilities. Using multiplication rule, you can say that these are 8 possible cases. Just let me write down. These are 1 success, These are two success. All success. Okay. 2, 4, 6, 8. Now this average is 0. This average is, what is this average? Can somebody tell me?
1 by 3.
Yes, because we are not worrying about probability and all. Just we are worrying about this capital X value. Later comes the probability. This is average, okay? 2 by 3, 2 by 3, 2 by 3, 3 by 3. Now this capital X can take values from these values 0, 1 by 3, 2 by 3, 1. Okay. What is the probability for X equal to 0? Out of the 8 choices, it happens only once. What is the probability for X equal to 1 upon 3? Out of the 8 possible cases, 1 upon 3 happens 3 times. What about possibility? Probability for X equal to 2 by 3. Again, upon 8, 3 only. Probability for 3 by 3, it is actually 1. Only once it is happening. Okay. Now I would like to draw the picture of our random variable, new random variable capital X. That also we should write here. Suppose if this is actually probability distribution of capital X. Okay. Here also I can write probability distribution of capital X. Okay. Now I have values 0 and 1 by 3. 2 by 3, 3 by 3. The probabilities, if you want to mark, it is 1 by 8. And this is also 1 by 8. Then 3 by 8. Okay, this is, that's it. Now I can go for n equal to 4. The same idea I should extend. What happens if n is becoming large and larger? That's my question. Let us look at only one more thing. N equal to 4. Instead of elaborately writing, we have no enough. We do not have enough space. N equal to 4. How many possibilities?
16.
16 possibilities. And what are the possible values for capital X? 16 possibilities we can write like, we have already written, we shall compare now. What are the possible values for capital X? Maybe just let me write down only those things. All fail or one pass. Is it okay? Only one pass. Or two examinations are passed. Just I used to shift these. Okay. Again, one fail. This is two pass, then three pass means one fail. One fail. See how many mistakes I do. all pass. These are the possible values for x1, x2, x3, x4. If you consider average, this capital X can take values from, can somebody tell me? Average of each class.
0.
Then
1 by 4.
1 by 4. Oh, actually it is 4 by 13. Okay, 4 by 16. Okay, that's what you say as 1 by 4. Okay, let us keep 16 in the denominator, so that for drawing the picture also it may be easy. If you write 1 by 4, that is also perfectly right. Then 6 by 16.
16.
Hi, we made a mistake. You see that? The mistake is that we are looking at the probability. We don't. I'm saying x can take values from here. Just I'm looking at x values. The average for this class is 0. The average for this class is 1 by 4. Yeah, you are right. You are right. I was wrong in this case, because you were saying the average value. I was discussing about the probability. You are talking about this average is 1 by 4. Okay. And here it is 2 divided by 4. Okay. Then 3 divided by 4. Then just 1. These are the values for capital X. Then I talk about the probability. What is the probability for capital X is taking? I'm sorry. What is the probability for 0? Capital X takes 0. Out of the 16 possibilities, capital X 0 means 0 is the average. That means 0 failure in all the exams. Only one possibility. Can somebody tell me what is the probability for 1 by 4?
4 upon 16.
4 upon 16, or you can write 1 upon 4 as I suggested earlier. What is the probability for x equal to 2 by 4? 2 by 4 is this 6 entries, 6 possibilities. Out of 16, 6 favorable cases. If you look for probability for x equal to 3 by 4, it is again 4 possible cases out of 16. And these probabilities we shall compute, then we shall be drawing in the picture as usual. What are the numbers? The numbers are 0, 1 by 4, 2 by 4, 3 by 4, 4 by 4. These are the numbers. If we look at the probability for 0, it is 1 by 16. For 1 also it is 1 by 16. For 2 by 4 and 1 by 4, okay, they look similar. Okay. For 1 by 4 and 3 by 4, it is 4 by 16. For 2 by 4, it is 6 by 16. Okay. This is the picture. Just look at only the pictures. Earlier, it was having only single peak and comes down. Look at the second picture. It goes up gradually and comes down gradually. Look at the third picture, it goes up gradually and has a peak and comes down. If I increase the number of examinations more, the pictures, how they will look like? That's the question.
Pascal's triangle.
Yes,
Pascal's triangle.
Pascal's triangle. Okay. How it looks like? Something like this you are saying? Is that?
Yes, sir.
Okay. If the variable is a continuous variable, how this curve will look like? That's the question. Suppose if I have continuous random variable, how they look like? That's what central limit theorem says. Central limit theorem says that you can it's not moving. Central limit theorem says that you can consider any random variable x1, any random variable x2, any random variable x3, and xn. Each of them follow the same distribution. Now you define capital X is the average. Now probability distribution of this x is a normal distribution. If n is becoming larger and larger, okay, or we'll say as n tends to infinity, as n becomes large, probability distribution of x becomes normal distribution. This is what we call as central limit theorem. At the random variables, all these random variables follow same distribution. Any distribution. It need not be normal. It need not be Bernoulli. It need not be binomial. Whatever may be that. And we define, or simply we define capital X, or simply let this capital X is this. As n becomes large, the probability distribution of X becomes normal distribution. This is one beautiful result because we don't worry about what distribution these Xi's are following. Here only uh, um, we have discussed Bernoulli random variables. Each of them has only two possibilities. And we look at when you increase the number of possibilities, when you increase the number of examinations, the picture is gradually going towards the normal curve. Here we discuss in terms of discrete variables. The same happens even if it is in continuous random variable. Because this is a Bernoulli random variable, we have only very slow appearance of the normal curve. Suppose if you consider another example, let us consider another example. Let us consider these random variables. Okay, throwing a die. Throw a die many times. Then this can have this can take these values. Not only that, this also can take these values. Not only one possible value. Okay, this can take these values. Now I'm going to compute capital X as usual. Suppose if you consider only one die, there is no change in that, because in that particular die, probability for the average value also is the same thing. Suppose if you talk about n equal to 1 through one die, what does it mean? You will be getting this. This is your first die. These are the values. And your capital X is the first die divided by 1. Again, they are the values. So you will be saying capital X can take values from this set. What is the probability for X equal to 1? 1 upon 6. What is the probability for X equal to 2? 1 upon 6, and so on. So if you want to draw the picture, you will be drawing X equal to 1, 2, 3, 4, 5, 6. Each of them is having 1 upon 6 is the probability. Same level, okay. Not only this happens, still X equal to 6 also 1 by 6. Now let us look at a 3 die case. N equal to 1 we have done, N equal to 2 we will do. This is different from Bernoulli, okay. 2 dice are through 2 dice. Meaning this can be X1, this can be X2. The average. The average is someone tell me how many possibilities are there? Possible outcomes.
36.
36 possible outcomes are there. You can have one here, here 6 possible outcomes, okay. For 2 again, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. 16 possible outcomes are there. Or you have to write like this. X1 in that side, X2 in this side. So here 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. In this way you have to write. Then what are the possible capital X values? Here 36 possible outcomes, okay. So capital X can take values. I think if I write that outcomes, Then only it is somewhat easy for everyone, I think. Just let me list down quickly. We are reaching time. One outcome, two, and you compute how many values are possible for capital X in the meantime. While I write this, any mistake will affect the result. 3, 5, what do I write? 3, 6. Maybe instead of writing everything, let me write down in this way. The last one is 6, 1, 6, 2. Yeah. Capital X can take values, maybe this visual if possible.
Ten values, sir.
Yes, 10 values. Take values from, let us write down the 10 values. The summation is 1, so the average is half. Is it okay? Oh, the summation is 2. Oh, I'm sorry. Summation is 2, so it is 1. Okay. Then this thing, okay. Then if you talk about this, summation is 3 by 2. So 1.5. Okay. Then this summation is 4. So it is average is 2. In this way, you are having 2.5, 2.6, 2. Not 2.6. I'm sorry. Till what number? 3.5.
6.
2, 4, 6, 8, 10. 11 values are coming. 2, 4, 6, 8, 10. 11 are there. Okay, 6 also will come. 6 plus 6 divided by 2. Is this fine? Now I want to draw the picture. One, 2, 3, 4, 5, 6. Not only that, in between also we have values. Okay. What is the probability for capital X equal to 1? What is the probability for capital X equal to 1 means the summation is 2. The probability for sum equal to 2 is only 1 out of 36. Do you understand this? The probability for 1 is, if capital X is 1, then this summation must be 2. Then this summation must be 2. Meaning in each die you should get the value 1. It is possible only 1 out of the 36 possibilities. So it is 1 upon 36. Similarly for this also 1 upon 36. Probability for X equal to 1. 1 upon 36. Probability for X equal to 1.5. If I need average is 1.5, summation must be 3. It is happening for 2 possibilities. So it is 2 upon 36. This is 2 upon 36, and this also. And this is 3 upon 36, and this also. This is 4 upon 36, and this also. This is 5. This is 5. This 3.5 occurs at the peak. Suppose if I need 3.5, then total must be 7. For total 7, it is 1, 6, 2, 5, 3, 4. Again, 4, 3, 5, 2, 6, 1. So out of 36, 6 possibilities are giving x equal to 3.5. So we get 6 by 36 there, 5 by 36. You see, this looks like a normal curve. 4 by 36, 2 by 36, 1 by 36. Irrespective of these probability values, we just look at the picture. It looks like having a single peak symmetrical about the peak. Whatever may be the experiment, if you talk about this average value, that new random variable will always follow a distribution that is a normal